Welcome to Pre-Calculus Notes 2.2, Finding Zeros of Polynomials, Essential Skill B2. In this lesson, we're going to look at factoring and solving high-degree polynomials and finding their zeros. First, let's look at a couple of definitions. As an example, look at the function f of x equals 2x minus 6. If we plug in 3, we get 0. This means 3 is a zero of the polynomial. Now look at the graph. Three is also an x-intercept of this graph. C is a zero of a polynomial, or sometimes called a root, if f of c equals 0. If c is a real number, then it is also an x-intercept of the graph. Let's put this in context and do a little warm-up at the same time. Please try example 1 on your own. Pause the video, and then I'll catch up and show the solution. There are two methods of doing this. I'll show you both of them, and you can decide which one you like better. According to the remainder theorem, we can take -3 and plug it into the polynomial, and the result will be the same as the remainder. Method 2 is simply using division. We'll set up synthetic division using -k as one of our numbers. Recall that the remainder must work out to 0, so we have an equation. Our zero remainder implies these two things. First, that x plus 3 is a factor of the original polynomial. It also implies that -3 is a zero of the polynomial. Take a look at example 2. When we divide this polynomial by x minus 3, we're seeing if x minus 3 is a factor of the polynomial. Try this. Here's my solution. Here's our quotient. The remainder was 0. Let's look at what this means. This tells us two things. First, that x minus 3 is a factor. But more specifically, p of x is equal to the product of x minus 3 with the quotient we found. In the last notes, we stopped with this partially factored form. Today we're going to finish the job and factor this second quotient polynomial. That will get p of x in fully factored form. We can read the zeros right out of this factored form. Here's an example you can try. I'm giving you one of the zeros of this polynomial. See if you can find the remaining ones. Use the same technique as above. Here's my solution. We were able to solve this problem relatively easily because I gave you one of the zeros to begin with. That gave us something to divide. What if we don't know any of the zeros? Bad news. If you're not given one of the zeros, then you're going to have to find one through trial and error. Fortunately, the rational root theorem gives us an approach. Every rational root must be of the form of factor of the constant over factor of the lead coefficient. Take a look just up the page. We'll put this in context. In example 3, 3 was the only rational root of p of x. The rational root theorem says that it must be of the form factor of the constant over factor of the lead coefficient, 3 and 1. So 3 must be a factor of 3 over 1, which it is. We'll use this to generate a list of candidates. This page has a walkthrough of how we're going to find all solutions to a polynomial when we're given no clues. Pause the video for a moment and read through this. Then we'll walk through it. Our first goal is to find one factor, one rational factor. Once we find that, we'll be able to solve the rest. Here's how we can generate a list of numbers to test. We form our list by taking these numerators in sequence and placing them over each denominator. also in sequence. So we have 2, 4, 6, 8 numbers to test. But realistically, it'll be fewer than that, since we're going to stop as soon as we find a successful zero. We found one with remainder 0. That means 2 is one of our zeros, and x minus 2 is a factor. Look at step 3 again now that we have some context. We look at the resulting quotient. If it's degree 2, which it is, we'll solve that using the AC method or the quadratic formula. If not, then we'll have to repeat the process. We'll see that in the next example. For now, we'll just solve this quadratic, and then we'll pretty much be done. So yes, we can have complex zeros. That's okay. As you can see, there's a lot going on with this procedure, and it absolutely has to be practiced so you can get good at it. Please pause the video and try the rest of the examples on your own. Get as far as you can, or try to complete them, and then resume the video. Here are my solutions. Thanks for watching.